Greetings to the Emertxe team and faculty. Myself Om Ghare, and today I will be presenting my project titled Real-Time EV ADAS Dashboard using STM32 Blue Pill and PICSimLab and the Python dashboard. This project was developed as part of my Embedded Internship 2026. Before we begin, let's understand what this project is all about. Modern electric vehicles are no longer just machines that transport us from one place to another. They have become intelligent systems that continuously monitor hundreds of parameters such as battery health, vehicle speed, motor performance, distance, and driver safety. Companies like Tesla, Mercedes-Benz, BMW, and Hyundai use advanced embedded systems to process all this information in real time and display on a smart digital dashboard. The objective of this project was to understand how such systems are designed by building a simplified educational prototype using the STM32 microcontroller. In our implementation, the STM32 reads the sensor input, performs the EV dynamics calculation, and executes ADAS algorithms, and sends all the processed information to the Python dashboard using our UART communication. Throughout this presentation, I will be explaining the complete architecture, the development process, the embedded firmware, and the ADAS logic, the communication protocol, and finally would demonstrate the working systems. And now let's begin by understanding the problem that inspired this project. And as we can see on this slide, the modern electric vehicle generates a huge amount of sensor data, battery management systems, motor controls, and obstacle sensor, temperature sensors, and many other ecosystems continuously. So this produces a large amount of telemetry that needs to be monitored in real time. The first challenge is the massive sensor data. A driver cannot manually observe every parameters while driving. The second challenge is the lack of centralized monitoring. When the information is scattered across multiple subsystems, it becomes difficult to understand the overall health of the vehicle. Another major issue is the late fault detection. If critical conditions such as overheating, low battery, or nearby obstacles are detected too late, they can compromise both the vehicle reliability and the passenger's safety. This leads to the final challenge, the safety concern. A modern vehicle should not only display information but also help the driver identify dangerous situations before they become critical. To address these challenges, the project proposes a real-time EV dashboard that combines the sensor monitoring, the EV dynamics, the ADAS functionality, and fault management into a single interface. Instead of presenting a raw sensor value, the system processes the data, detects the unsafe condition, and provides meaningful visual feedback through a live Python dashboard. Now that we have understood the motivation behind the project, now let's look at one of the most important components, the Advanced Driver Assistance System, that is ADAS. As shown in the illustration, the ADAS continuously monitors the vehicle's surrounding using sensors and provide warnings whenever a potential dangerous situation is detected. The first feature is forward collision warning. The front sensor continuously checks the distance to obstacle. If the object comes too close, the system alerts the driver before a collision occurs. The second feature is the blind spot detection. The vehicle approaching from the left or right side are often difficult to notice through the mirrors. Side sensors monitor these regions and notify the driver whenever another object enters the blind spot. The third feature is the parking assistant. During low speed maneuvers, the system measures distance around the vehicle and helps the driver park more safely. Finally, the project also implements time to collision or the TTC. Instead of considering only the distance, the system eliminates how much time remains before the impact based on the current speed and the obstacle distance. This makes the warning system more intelligent. Although commercial vehicles use radars, cameras, and lidars, our prototype would demonstrate the same engineering concepts using ultrasonic sensors. Now this slide gives an overview of the complete architecture of system. The process begins with the sensor layer, where various inputs such as throttle position, battery level, motor parameters, and obstacle distances are collected. These inputs are sent to the STM32 Blue Pill, which acts as a central processing unit of the project. It receives all the sensor data, performs pre-processing, and manages the execution of different software modules. The processed information is then processed to the EV dynamic engine. This module simulates important vehicle parameters such as speed, battery, SOC, that is state of charge, power consumption, and estimated driving range. Next comes the ADAS engine, which analyzes the ultrasonic sensor readings to detect nearby obstacles, calculate collision risk, and generate safety alerts. Finally, the process data is transmitted to the Python dashboard where all the information is displayed through gauges, indicators, and warning messages. Although this is a simplified prototype, the architecture closely follows the layered design philosophy that is used in the real automotive embedded systems. Now, the common question is how closely this project resembles to the real automotive system. The answer is this hardware has been simplified, but engineering principles remains the same. On the left-hand side of the comparison, we have the technologies commonly found in commercial electric vehicles. Production vehicle use dedicated electronic control units, that is ECUs, whereas our project uses the STM32 Blue Pill as the main controller. Instead of the high-speed CAN bus network, our prototype communicates using UART, which is simpler and well suited for our embedded learnings. Commercial ADAS systems rely on radar and LiDAR for environmental sensing. In our prototype, we use the HCSR04 ultrasonic sensor and potentiometers to simulate the vehicle inputs. Similarly, instead of commercial digital instrument clusters, we have developed a custom Python dashboard that displays all the vehicle parameters in real time. So while the hardware platform is simplified, the workflow of sensing, processing, communication, and visualization follows the same principle used in modern automotive embedded systems. Now that we have understood the overall architecture, now let's look at how the project was developed step by step. I followed a structured development roadmap consisting of multiple phases where each phase built upon the previous one. The first phase was the environmental setup, where I configured the STM32 Cube IDE for firmware development and PICSimLab for simulating the hardware environment. This provided a stable platform for coding and testing without requiring the physical hardware. The next phase involved configuring the GPIO peripherals, which are responsible for interfacing with sensors and other external components. After that, I implemented the ADC, the analog to digital converter, to read analog values from the potentiometer. This potentiometer simulates the real-world inputs from the accelerator position and the throttle. Once the sensor inputs were available, I developed the EV dynamic engine, which calculates the important vehicle parameters such as speed, motor torque, battery state of charge, and driving range. The next milestone was implementing the ADAS module, where the obstacle detection, collision warning, blind spot detection, and the parking assistant logic were developed. After ensuring the vehicle logic was functioning correctly, I implemented the fault detection system to identify abnormal conditions and generate different level of alerts. The processed information was then transmitted using the UART communication to a computer running a Python application. Finally, I built the Python dashboard, which displays all the real-time telemetry in an interactive graphical interface, followed by the complete system testing to validate the integration of all the modules. The structure roadmap that every subsystem was tested individually before being integrated into the final project. This slide summarizes the hardware and the software technologies that were used to build the project. Together, these tools form a complete embedded systems development for workflow from firmware development to the real-time visualization. Now let's begin with the hardware. At the heart of the system lies the STM32 Blue Pill based on the ARM Cortex M3 microcontroller. It is responsible for reading the sensor data, performing calculations, executing the ADAS algorithms, and communicating with the dashboard. For obstacle detection, the project uses the HCSR04 ultrasonic sensors, which continuously measure the distance between the vehicle and the surrounding objects. To simulate the driver inputs such as the throttle and speed, potentiometers are used as analog input devices. These inputs are converted into digital values using these STM32's ADC. Instead of building the prototype, the system is simulated using the PICSimLab, allowing a rapid development, debugging, and testing a virtual environment. On the software side, the firmware is developed on STM32 CubeIDE using the Embedded C and STM32 HAL library, which simplifies the peripheral configuration and hardware interaction. Finally, Python and PySerial library are used to receive the UART data from the STM32 and display it over a graphical dashboards. Now we come to the most important module of this project, the EV dynamic engine. The module is responsible for simulating an electric vehicle behaves under different driving conditions. At the center of the diagram, we have the vehicle, while the surrounding parameters represent the key calculations performed by the module. The process begins with the driver's throttle input. Based on how the input, the system calculates the motor torque, which determines how much force is available to move the vehicle. Using this torque, the software estimates the vehicle speed and calculates the corresponding power consumption. As energy is consumed, the battery state of charge, or the SOC, gradually decreases. This value is continuously updated to reflect the remaining battery capacity. Using the available battery energy, the system also estimates the remaining driving range, giving the driver an idea of how far the vehicle can travel before recharging. The module also supports different drive modes and regenerative braking, which influences how quickly the battery discharges or charges during an operation. At the bottom of the slide, you can see the example values representing the vehicle's peak power, estimated range, and the battery percentage. These values demonstrate the type of information that would typically be displayed over the EV dashboard. Overall, the EV dynamic engine transforms the simple sensor input into the realistic vehicle behavior, making the dashboard much more meaningful than simply displaying the raw values. One of the key advantages of electric vehicle is that they adopt their behavior depending on the selected driving mode. This slide shows the three operating modes implemented in the project along with the concept of regenerative braking. The first mode is the eco mode. In this mode, the vehicle prioritizes the energy efficiency, motor torque is reduced, power consumption is minimized, and the battery lasts longer, making it suitable for city driving. In the second mode, the normal mode, which provides a battery balance between the performance and efficiency, it delivers a standard throttle response and ideal for everyday conditions. Finally, the sports mode focuses on the maximum performance. The motor produces higher torque, resulting in quicker acceleration. However, this increases the performance, leading to the higher battery consumption. The lower part of this slide illustrates the regenerative braking of the electric vehicles when the driver applies the brake. The electric motor temporarily works as the generator instead of consuming power. The vehicle's kinetic energy is converted into electrical energy and is sent back to the battery, helping recharge it while slowly the vehicle slows down. Although the implementation is simplified, it demonstrates how energy recovery improves efficiency and extends the vehicle's driving range. This feature is the reason why electric vehicles are significantly more energy efficient than the conventional petrol or the diesel vehicles. Now let's look at the intelligence behind the safety features, the ADAS engine. This module continuously analyzes the sensor data and helps the driver by identifying potentially dangerous situations before they become critical. The first feature is the obstacle detection. Ultrasonic sensors continuously monitor the area around the vehicle and measure the distance to nearby objects. Using this information, the system performs the collision warning. If an obstacle comes within a predefined space threshold, the driver receives an alert before the collision occurs. The third feature is the blind spot detection. The side sensors monitor the area that are difficult for the driver to observe, helping prevent the unsafe lane changes. Next is parking assist. During low speed maneuvers, the sensor provides continuous distance measurements, making parking safer and more convenient. Finally comes the time to collision or the TTC. Rather than looking only at the distance, the TTC considers both the vehicle speed and the distance to obstacle to estimate how much time is remaining before the impact. This provides a way more intelligent warning system. The same distance may represent a very different level of risk depending upon how fast it is traveling. The commercial vehicle use the radar, camera or lidar, but this successfully demonstrates the same decision-making process used in the using the ultrasonic sensor and the embedded software. Now that we have discussed the EV dynamics and ADAS modules, let's move on to the another critical component of the system, the fault detection and alarm system. As the name suggests, this module continuously monitors the health of the vehicle and determines whether it's operating under safe conditions. If you look at the flow diagram on the left, you'll notice that the process starts with vehicle parameters. This includes inputs such as motor temperature, battery state, state of charge, vehicle speed, obstacle distance collected from the sensors. The next stage is the threshold evaluation, where each parameter is compared against predefined safe operating limits. For example, if the motor temperature exceeds a safe value of, or the battery level becomes critically low, the system immediately identifies it is an abnormal condition. Once a threshold is exceeded, the fault detection logic determines the type of fault and passes it to the alarm classification module. Here, the fault is assigned a severity level based on how critical it is. Finally, the driver warning stage informs the user through dashboard alerts, warning messages, and visual indicators. On the right side of the slide, you can see the 4 alarm level implemented in our project. The normal state indicates that all the vehicle parameters are safe within an operating limits. The advisory level informs the driver about conditions that require attention but are not immediately dangerous. The warning level indicates an unsafe operating condition that should be corrected soon. Finally, the critical level represents the severe conditions requiring immediate action to prevent the damage or ensure safety. This structured fault management approach ensures that the driver receives meaningful information instead of simply displaying the raw sensor values. Once all vehicle calculations are complete, the processed information must be transferred from the STM microcontroller to the dashboard. This is where UART telemetry plays an important role. As shown in the communication diagram, the STM32 Blue Pill acts as the source of the all vehicle data. After processing the sensor input and running the EV dynamics and ADAS algorithms, it prepares a structured telemetry packet. This data is transferred using the UART protocol, which is one of the simplest and most reliable serial communication methods used in the embedded systems. The UART data is then transferred over a serial connection to the computer, where a Python application continuously listens for incoming packets using the PICSerial library. After receiving the data, the application extracts parameters such as vehicle speed, battery SOC, motor temperature, driving range, ADAS status, and alarm information. Finally, these values are displayed through a real-time dashboard, allowing the user to monitor the vehicle graphically instead of just interpreting raw serial data. At the bottom of the slide, you can also see an example of the telemetry packet, which contains a important parameter transmitted by the STM32. This communication pipeline demonstrates how embedded firmware and desktop software work together to create a complete real monitoring system. Now in this section of the video, I will give a demonstration of our project, how it works from start to end. So basically I have opened my STM32 Cube IDE. So here we can see this is the EV dashboard project. So in this we have files like main.c, EV controller, ADAS, fault.c to check all the parameters of our project. So make sure you have generated the .bin file before we move on. So just right click on your project, then go to properties, then go to C++ build, go to settings and go to MCU/MPU post build outputs. Make sure you have selected the convert binary file and convert hex file options, then apply and close, which I've already did. So let's move on and open our PICSimLab. So here we'll just load our bin which we generated. Once you click on the build option in the STM32 Cube ID, you just get this bin file. So once we dump this bin file, here you can see the virtual terminal have started showing us output, and here also we can see our components and our microcontroller working as usual. So here we can also lower our value in which the red LED starts glowing. So now the red LED is off. So here we can see we have the accelerator, the brake, the SOC, the temperature components. Here is the front ultrasonic sensor, here is the left, and here is the right. These are the side, the blind spot detections, and here is the avoidance collision for front side, and here are the LEDs. So let's just open our virtual serial port emulator. So what we have to do is we have to configure the PICSimLab to COM5. Here we click save and configure it to the COM5. And here we have to open the virtual serial port application, then Then we have to go to device, create a new device, then select the virtual pair and click next. Then select the COM which is available. So I've already done. I've selected my COM5 and COM6. So you also do the same. So once we click finish, we get such an interface where COM is connected. The virtual COM port is created. So we have this code for the Python dashboard which shows all the graphical format of the sensor output. So we'll just enter this command. So now we can see our dashboard has been created on our COM port 6. Now here you can see the dashboard which is created. So here we can see we have our EV dashboard with the components. So if we increase the distance, here you can see in live the distance is increasing or decreasing. This is live telemetry data. So here you can see the vehicle has came very close. Now we can see the blind spot detection is also working as intended. This shows the vehicle, which is how close it is. We can also increase or decrease the temperature by increasing the acceleration rate. So the speed starts increasing with the constant acceleration. Here we have applied brake, so it starts decreasing. So here you can see it becomes 6. This is at a constant rate, so slowly the speed would increase or decrease. So now it became 5. So if we keep it for a while at a constant acceleration, the speed would start increasing. Now if we increase the temperature, here you can see the LED has been blown, and here also on the EV matrix we can see the temperature which is 105 degree. That's more. And now here you can see the temperature is at a good rate. So so you can see the acceleration is at 93%, which decreases as we configure the potentiometer. So this was all the EV dashboard, and here we can see alarm is none. So anything if it happens, the alarm shows. See if the alarm has at a critical position. Now here the alarm is in warning position, and if the car is out of the risk, the alarm is at none. So this was the overall demonstration of this project, how the telemetry works. This slide brings together all the individual modules that we discussed in the previous section, at how it works as in one integrated system. So we use the PICSimLab to simulate the embedded hardware and change the sensor values such as throttle, the accelerator, the brake, the ultrasonic sensor, and in the center we had the serial monitor which displayed the raw UART telemetry which was transmitted by the STM32. This allows us to verify the communication. On the right we can see the Python dashboard which we saw in the demonstration section, which converts the incoming telemetry into visual information such as speed level. So then comes our workflow, which shows all how the sensor input is generated from the STM32 firmware which we wrote, the ADAS logic, the dynamic engine, and the vehicle parameters. Then comes the final dashboard which showed the visuals of the vehicle condition. This integrated workflow demonstrates the embedded firmware, communication protocol, and visualization methods in the automotive monitoring system. Every engineering project comes with its own challenges, and this project has no exception. So developing a real-time embedded system requires careful planning and testing. So one of the biggest challenges was maintaining the real-time schedule, ensuring that all the software module is executed at the correct intervals without affecting another. Another challenge was the sensor synchronization, since the data from multiple sensors had to be processed continuously to maintain accurate system behavior. The reliable UART packet transmission was also an important factor. Finally, debugging the embedded software requires systematic testing. So what we can do to improve this? So instead of UART communication, the system can also implement CAN bus. There are additional sensors such as GPS, cameras, LiDAR, which would be effective. Also, machine learning can be implemented. Finally, the cloud connectivity and over-the-air updates would also enable the remote diagnostic and data logging firmware updates. So although the current implementation can be enhanced and transformed into much more advanced automotive platform. Now I would like to briefly summarize what I've achieved through this project. I've successfully developed a real-time EV ADAS dashboard using the STM32 Blue Pill, PICSimLab simulators, and a Python dashboard. The project integrates sensors interfacing like EV dynamics, ADAS features, fault detection, UART communication, and real-time visualization. Working on this project gave me valuable hands-on experience in embedded C programming, STM32 peripheral programming, real-time communication, and automotive embedded design. I would like to express my sincere gratitude to Emertxe Technologies for providing me with this internship opportunity and for their continuous guidance and support throughout this project. The experience has significantly enhanced my practical understanding of embedded systems and of automotive technology. So, thank you all for giving your time and attention.